Thank you for returning for our treatment of ray diagrams with mirrors. We're moving on from the simpler convex mirror system, which was, of course, slightly more complicated than the plane mirror. And let's see, here's a plane mirror. The plane mirror shows a pretty big camera here. Here is our convex mirror, the one that we decided always shows something smaller than in a plane mirror. And this one over here is our new one. This one is caved in. This is a concave mirror. Now this one is more complicated than either of the last two. And that is because it behaves differently at different regions. Right now, this camera, well, first of all, here's the shape of my hand, but up here, it's upside down. Okay, so we're finally going to see an image which is inverted. Also, if we look at something which is closer to the lens, then, oh man, it's huge. Okay, it's definitely different. And that's the first case that we're going to look at. We're going to look at the case where we are closer than the focal point. Okay? The camera at the moment is farther than the center point of the center of curvature of this lens, so it behaves differently. If we were to bring this in closer, it is still, if I can keep it there, which I can't really, there we go. If I keep coming closer, it gets bigger and bigger until at some point things get really weird and no longer focus the way you expect them to. All right, which we're going to investigate that also. But for right now, we're going to look at that case where it made an enlarged version. So we're going to start with our central axis, our axis of symmetry. Right down the middle of our page. We are going to have our image over here on this side in the real world. That's the virtual world over there. We want our mirror to be caved in, so we want our center point over here. So I'm going to put my center point way the heck over here. I'm going to draw this thing as big as I can make it so that it crosses through a line so that I can count off squares, which just makes life easier instead of having to grab a ruler. That's why we like graph paper. Now, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Coincidental. I think that's one of the common ones where it hits a square. So I need to be 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half boxes out for my focal point. Focal point, center of curvature. The left side of the mirror is the real world. The right side of the mirror is the virtual world, as indicated by the cross-hatching. Also, notice again that it is perpendicular to the central axis at that location. All right, now we want to be closer. Now we knew it was enlarged, so I'm not going to make it too terribly big. So I'm going to only make my object 4 boxes tall. And since I'm interested in a distance between the focal point and the axis, I'm going to put somewhere in the middle of it. Okay, we'll consider the extremes afterwards, but for right now, put it about in the middle. Now, our rays. The first ray that we draw is the one which is parallel. So it comes out here. Now, it's parallel as it leaves our object, but then it goes through the focal point. This time the focal point is in the real world on the left-hand side of the page. But it looks like it came from back here. Okay, so I'm going to extend that one out. It looks like it's coming this way. Okay. Our next ray that we can draw is the one coming through the center point. And if we wanted to, we could draw a line to that center and show that the angle of incidence equals the angle of reflection, which is how all mirrors work. Okay, from our center point, looks to me like it's going to cross out here. And it looks like my light's coming in this way. I'm suspicious of an image out over here, but let's try another one. Now this first one was my P ray. This one is my C ray, the one that went through my center point. Remember, the P ray is the one that leaves parallel, then goes through the focal point. If I wanted to, I could do the focal point one. Now, I'm going to start being suspicious that this might be the one that doesn't line up with the other ones because it is farther from the central axis. Okay, so it goes up there, and then it goes out to the side. Now, it's not quite crossing the other guys, and that's making me a little bit nervous. It's making me want to have another ray to count on, because it didn't quite cross with everybody else. Okay, but the light definitely does look like it's diverging from that central point region there. Okay, our last ray that we can draw is the one that goes through our midpoint. And in my opinion, the one that goes through the midpoint is probably the most accurate because it hits down here where the extreme curvature hasn't messed anything up. Now remember, for our midpoint, we're going to count up how high we are here. 1, 2, 3, 4. That's the height of the object. We're going to count below that. 1, 2, 3, 4. So it's going to go through that point. So the ray of light from the tip of our object strikes the midpoint of the mirror. Okay, that's why we call it the mid-ray. And then it comes back through this one. Oh, man, this is really out there. And this is what we get. We get this a lot, where things don't quite agree with each other. Okay, so all I know is that somewhere in this vicinity, I'm going to get an image. Now I learned some stuff from that. I mean, one thing that we learned from this is that it's, and I'm just going to put it about in the middle of it. One thing that we learned from this is don't draw too many rays. Get a couple of them to cross and live with it, because these first two cross within that general circle. Right? That would have been fine. You don't have to do this kind of thing to death. Right? And it's very unlikely that they will all cross at exactly the right point. All right, but we can calculate it. All right, so that means we need to make some measurements. Now, the only measurements, I cannot measure anything about my image and use that to calculate where should my image have been. So instead, all I can measure is the distance to my image. I'm sorry, distance to my object. The distance to my object was 1, 2, 3, 4, 5. Was positive 5. It was in the real world. The distance to my focal point is 1, 2, 3, 4, 5, 6, 7, 8, 9.5. 9.5. Again, positive. The distance to my center of curvature doesn't show up in the calculations. The only calculation it shows up with is how to find your focal point, because the center of curvature is always equal to twice the distance to your focal point. The last thing I need is the height of my object. 1, 2, 3, 4. And the height of my object is positive 4. Now, from this, I can figure out where my object should be located at. I'm going to find the distance to my image. And I'm going to find that with my mirror equation. 1 over the distance to my object plus 1 over the distance to my image is equal to 1 over my focal length. I want the distance to my image. 1 over the distance to my image equals 1 over my focal length minus 1 over the distance to my object. Now I substitute in some numbers. 1 over 9.5, and it's positive, minus 1 over the distance to my object, which is also a positive, 5. Okay, now I grab a calculator, and I put in 9.5, find the inverse of it, and from that I subtract off the inverse of 5, or I just know that in my head and subtract off 0.2, and we end up with 1 over the distance to my image is equal to negative 0.095. Okay, I'm going to take the inverse of that. And I get that the distance to my image should be negative, in other words, on the virtual side, 10.6 when I round it off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.6. It should be here. Well, let's figure out which ones are crossing there. And then from this, we can interpret which of our rays are most of the time accurate. All right, so it's along there someplace. Okay, and that looks to me to be about where the center ray was crossing this mid-ray. You see how I really like this mid-ray? It seems to always be the most accurate one. Okay, or it could be where the parallel ray, yeah, I bet you it's this one, where the parallel ray hit the, well, actually the parallel ray hits the mid-ray a little ways out here. Okay, but I like that mid-ray. I think that one's one of the most accurate that we can draw. Okay, now let's figure out how high it's supposed to be. Since magnification equals height of your image over the height of your object, which is equal to the negative of the distance to your image over the distance to your object, your image height, h sub I, is equal to negative the height of your object multiplied by the distance to your image over the distance to your object. Be careful with your negatives. All right, negative 4 multiplied by the distance to my image, which is a negative 10.6, divided by the distance to my object, which was 1, 2, 3, 4, 5. And when all is said and done, the height of my image should, let's check, 4 times, I'm going to ignore the minuses because they're going to cancel, 2.6 divided by 5, and I get that my image should be 8.48, I'm going to call that 8.5 boxes tall. And let's see, 1, 2, 3, 4, 5, 6, 7, 8.5. Wow. Totally agreed, like I said, with that midline, because that one is the closest to the axis of symmetry. That's the one that is least messed up by the fact that this is a circular mirror or a spherical mirror instead of a parabolic mirror. Parabolic mirrors have a focus which is good throughout the entire mirror. Circular mirrors are not good throughout the entire mirror. Now, if I was just making a quick sketch, I wouldn't have drawn half these lines. I would have picked 2, I would have seen where they crossed at, and I would have called that my approximate location and my approximate height. And within a few percent error, it would be right. I hope you followed all that.